In this video, I'm going to show you how we find stationary points using calculus and exactly what a stationary point is, and some of the applications. I'll start looking at some of the applications. Now, to start with, this seems pretty self-explanatory. It's fairly straightforward and not all that sort of spectacular in nature, but it does become really, really important as we go further into our applications of calculus, particularly when we start talking about motion of a particle, which is quite a large part of where our calculus functions come in. So we'll make a start and see how we go. Okay, so the definition of a stationary point is simply that it is a point where the gradient is zero. Okay, so we are either talking about a maximum here, or a minimum, or you could possibly have a point of inflection. Okay, so in terms of mathematical definition, it's where the derivative of the function is zero. Okay, so if you differentiate a function and then find where that value, for what values of x that function is zero, that's where you find your stationary points. Okay, so let's jump straight into a couple of examples. So the first one, we've got finding stationary points for the following functions. This one's fairly straightforward, and then this one has a restriction that says t has to be greater than zero. So let's do the first one, and then we'll come back. So the first thing we need to do is differentiate, because we're looking for where the gradient is zero. Right, so that's going to be 12, take 4x. Okay, so let the gradient equal 0. 12 take 4x. X is 3. Okay, now where it says stationary points, that means find the coordinates, not just the x value. Okay, so when we've done that, therefore stationary point at 3, and if you put 3 back in there, you should get 27. Okay, so you can check that. Right, for part B, we've got the derivative first, so we're doing dp in terms of t, dp dt. Okay, that's going to be 6t squared minus 10t minus 4. We want to know when does that equal 0. So 0 for what values of t. Now when you solve that, what you get is you either get 2 or negative a third. 2 or negative a third. Now usually that wouldn't be a problem, but we've been told that t must be greater than 0, so we can discount that one. Okay. Therefore we're only looking at t, and if you plug that back into your original function, the stationary point will then be at 2, 1. Okay, so remember that when you're finding the stationary points, it's the stationary point of the original function. Okay, so for a, we're putting the x value, x equals 3, back into here, and for b, we're putting t equals 2 into this function, not back into there. Okay, so that will give you your stationary points. Alright, let's have a look at another one. So this one's slightly different, and now we're starting to draw together a few different aspects of how we go about solving. So the first thing we've got is we've been told that this curve passes through this point, okay, which happens to be the y-intercept. Okay, we're also told that it has a stationary point at 2, 7. So let's deal with this first. So if this passes through the y-intercept, then that clearly means that that's 5 when this is 0, and this is 0, and this is 0, and this is c, so obviously c must be 5. Okay, I don't expect you to need to do that, but just demonstrating where it comes from. Okay, now there's actually 2 bits of information here. Okay, the first one is that it must go through this point, the function must go through 2, 7, so this is a point on the curve. Okay, but it also tells us that it's a stationary point, so that means that the gradient at that point is 0. Okay, so what that's going to allow us to do, because we've still got 2 variables, so we need 2 equations so we can solve that. So we can substitute this into the original function. So if we say 7 equals 2 cubed plus a times 2 squared plus b times 2 plus c, which we know is 5. Okay, and then over this side, if we differentiate it, dy dx 3x squared plus 2ax plus b. Okay, now we let that equal 0 when x equals 2. 3 times 2 squared plus 2 times a times 2 plus b. Okay, so if you sort of switch those all around, do some simplifying. 13 plus 4a plus 2b, or not 2b, sorry, I can't help myself. And this one is 12 plus 4a plus b. Okay, whack that into your class pad to solve your simultaneous equations, but you can do it by hand. It's fairly straightforward, they're just nice and linear. But if you're looking to do it quickly, class pad is your friend. So a will give you minus 9 over 2, b is 6, and we already know that c is 5 from there. Okay, so the question says find a, b and c, so this is sufficient. You don't need to restate the equation with these values in, as long as you've got a equals negative 1 and 2, b equals 6 and c equals 5, then that's good enough. Okay, so make sure that you understand what information you can get out of these questions, because sometimes, like this one's actually two separate bits of information that we need to use here. Okay, so we know we need to differentiate and let that equal 0, and then we're only interested in the x value there. The y value becomes no longer relevant because we're not talking about this function anymore. But when you're talking about that as a point on the curve, then you're using both those. Okay, if you need to look at, once you've got this answer, look at plotting this and then see what's going on. So you can check that's the y-intercept, you can confirm that there is a stationary point at that point. Okay, so spend a little bit of time getting your head around this, because this understanding of this type of question is really important. Okay, so in terms of types of stationary points, there are 3 that we'll talk about at the moment. There's a couple more that we'll go into in the next video. So these 3 are local maximum, local minimum, and the stationary point of inflection. So a local maximum and minimum, these are known as turning points. Alright, so what that means is it's not necessarily the maximum of the function. It might be, as in the case of a parabola, but it might not. But it is a local. So within the sort of restricted domain, it is the local maximum. So A, for example, is a local maximum. Local max. Okay, here, because it's its maximum value. It's obviously not the maximum value of the function, because we can see the function continues on up this way somewhere, and it might continue indefinitely up here. Right, so it's not the overall maximum, but it is a local maximum. This here is a local minimum. Okay, so those are both turning points where the gradient changes, and the point of inflection is C, so that's where you come to a gradient of 0. So here we've got negative gradient, and then it's 0, but then it still carries on negative. So the difference between inflection and a turning point is with the turning point the gradient changes from positive to negative, so positive to negative or negative to positive. Okay, whereas with the point of inflection the gradient doesn't change. It's negative here and it's still negative. Okay, so gradient changes, and when I'm talking about change, I mean it changes from between positive and negative. So positive to negative or the other way around. Stationary point of inflection, gradient doesn't change. So it's either, it doesn't change. So it's either positive through 0 and then positive again, or negative through 0 and negative again. Okay, so the nature of the stationary point is, what we mean by that is it a maximum, or is it a minimum, or is it an inflection? Okay, so if you're asked for the nature of a stationary point, that's what we're getting you to find out. And you determine that by examining the gradient on either side. So, like I just mentioned on the previous screen, okay, if you look at it whether it's positive or negative, the value, it doesn't matter. We don't care how positive or how negative it is, just whether it's positive or negative. And we look at that to either side of the point. So if you know that this function has 2 stationary points, then and you can find the locations of those, then you can just come over this way, find a point over here, and just determine whether the gradient is positive or negative, and over this side, and that will tell you whether it's a maximum, minimum, or inflection. Okay, so in this case, as you can see, we've got positive gradient here, it's sloping upwards to your stationary point where the gradient is 0. Okay, then we have negative gradient sloping downwards to your other stationary point, and then positive again. Okay, so that gives us an idea of the overall shape of the function. Alright, so let's look at this one. So this function, or sorry, this question says, for the function given, find the stationary points and state their nature. Okay, so the first thing we need to do is differentiate. F prime x, 9x squared, take 4. Okay, now we know when stationary points occur, the gradient must be 0. 9x squared minus 4, and that will give us x is plus or minus 2/3. Okay, whenever you're finding points, you need coordinates, so therefore stationary points occur at minus 2/3, and if you just plug that back into this function, you get 25 on 9. And the second one is positive 2/3 and negative 7 on 9. Okay, so those are your 2 points. Now, the easiest way to sort of determine what's going in between, other than graphing it with your calculator, is to set up a little table. So we want to know, what is the value of x? What is the value of f of x? Okay, is it positive or negative? And therefore, what is the slope? So we can draw like a little sort of slope diagram. So if we do this, and we're going to have a number of columns here. You have, well, for this one we'll have 5. Okay, now we know at negative 2/3, so when x is negative 2/3 or 2/3, we know that the value of f prime x is 0, so that means the slope is horizontal. Okay, so that means flat, not negative, it's just flat. Okay, so we can just arbitrarily pick any point to either side and pick something easy. So negative 1 would be good, 0 in the middle, and 1. Okay, something less than negative 2/3, something in between, and then something bigger than 2/3. And then all you do is plug that back into here. So if we want to find f prime of negative 1, f prime of 0, and f prime of 1. Okay, and if you work those out, you get 5, negative 4, and 5. Okay, so this is where you're using a function to find feature on your calculator can save a little bit of time. Okay, so what that means is that's positive there, positive 5, so it's just positive. We don't really mind what the value is, we just want to know is it positive or negative. That's negative there for negative 4, it's positive. Okay, so if that's positive, it means it's sloping up, negative sloping down, positive sloping up again. Okay, so what that tells us, we know this is a cubic. Okay, we know now that it's got 2 stationary points and that it's going up, stationary down, stationary up, so the shape is like that. Okay, it doesn't tell us anything about where that occurs on the on the axes, because we don't know what the x-intercepts are. So if you wanted to sketch this accurately, you would need to then solve for the x-intercepts, which we spent quite a lot of time doing back when we were doing polynomials. But for this, in terms of just stating the nature, that's what we need to look at doing. Okay, so this tells us that this must be a maximum. This is this point, local maximum, local minimum. Okay, so you can go back here and say that's local max, and that's local min. So you have found the stationary points, and you've stated their nature. So that's your question there. Okay, so in summary, a stationary point occurs when the gradient is 0. Right, it's fundamental. Make sure you remember this. It will come in handy with many questions. Okay, so gradient 0. Local maximum and minimums are known as turning points, right, which we're already reasonably familiar with from all our work with quadratics and cubics. We can find them by checking the gradient to either side of a stationary point. So that little table that I showed you in the previous example is quite handy to do that. It sets it up nice and systematically. Makes it easy for the person who's marking your work, which is always a good thing. And then a stationary point of inflection either goes positive 0 positive or negative 0 negative. So what I mean by that is we have positive gradient goes through 0 and it's positive again, or negative gradient goes through 0 negative again. And those are your stationary points of inflection there.